It circles the planet 16 times a day, 350 kilometers above our heads.
Okay, great news, Rex. Thanks a lot.
The International Space Station is the largest man-made object in the sky and is home to a crew of 10 astronauts. They are carrying out experiments to investigate how life might be moved off the planet.
I'm going to give you some sequence here. Stand by.
Such work may one day allow us to colonize the moon or even Mars. Four landmark spacecraft lie behind the success of the International Space Station. At the heart of each structure lies a major technological breakthrough that allowed engineers to build bigger spaceships. One by one, traveling up the scale, we'll reveal the stories behind these incredible machines. 5 ingenious leaps forward that enabled space stations to grow from big to bigger into the world's biggest.
Ten, 9, 8, go for main engine start. 7, 6, main engine ignition. 4, 3, 2, 1, 0, and liftoff of Space Shuttle Atlantis as Columbus sets sail on a voyage of science to the space station.
Houston now controlling Atlantis on.
February 2008. Space Shuttle Atlantis begins a 13-day mission to deliver the latest components to the continually evolving International Space Station.
Kennedy Space Center traveling 2,000 miles an hour.
For the past 11 years, astronauts have been piecing together the structure in space. By the time it's finished, it will consist of 14 pressurized modules, including science laboratories and living quarters, and will weigh 400 tons.
1 meter to go. Copy.
At a cost of £60 billion, it is the most expensive and challenging construction project ever undertaken. To understand how it became possible to build something so ambitious, we must travel back in time. Our story begins at the height of the Cold War. To build the world's first space station, Salyut, Soviet engineers first had to conquer the pull of gravity.
Over. The Eagle has landed.
In June 1969, America beat the Soviet Union in the race to put a man on the moon.
Go ahead, Mr. President. This is Houston out.
Hello, Neil and Buzz. This certainly has to be the most historic telephone call ever made.
The Soviets were determined not to be beaten again. They wanted to put a man in space for longer than ever before. Scientists didn't know how the human body would cope over time in this extreme environment. So they decided to put a laboratory in space to find out. Salyut would hold a crew of 3 cosmonauts. The pressurized compartments would have a control room and living quarters. The plan was for the cosmonauts to spend 3 weeks there. But to stay in orbit that long, Salyut would have to travel at 28,000 kilometers per hour for the duration of the mission. Astronaut Leroy Chow, veteran of 4 space station missions, knows the danger of taking your foot off the gas.
If you're not going fast enough and you go up into space, you're just going to fall right back down. So you've got to get into what we know as orbital velocity, and in that way, the force due to acceleration is going to be exactly balancing the gravitational pull. When those forces are equal, then the object will stay that distance from the Earth or whatever object it's orbiting.
To reach orbital velocity, 28,000 kilometers per hour, Russians strapped Salyut to a Proton rocket. Once the rocket was in orbit and Salyut released, there would be nothing to stop it maintaining this speed. Space is a vacuum. There is no air resistance to slow it down. But unfortunately, this vacuum is not completely empty.
Well, in principle, if you didn't have any friction at all, then you would, once in orbit, you would stay in orbit. In the case of the Earth, we have an atmosphere of air, of course, and so even at an altitude of several hundred miles, there's still some air molecules up there.
Even molecules of air hitting Salyut would be enough to create drag and slow the spacecraft down. If the speed dropped below orbital velocity, gravity would have pulled the craft back to the Earth, with disastrous effect. But using a rocket to boost Salyut was risky. They go off with a bang and burn out quickly. An uncontained blast could have sent Salyut careering into deep space. Engineers needed a rocket they could keep in check. The answer came from an unexpected place. During the Korean War, the US Army wanted to move their soldiers quickly around the battlefield. Engineers came up with a gizmo straight out of Dan Dare. A rocket pack. The Rocket Man could hover because his jet was powered by a chemical reaction, which he could easily control. Chemist Andrew Shidlow demonstrates how to generate thrust from a simple chemical reaction.
When hydrogen peroxide decomposes, it releases oxygen and water in a form of steam. As I press the syringe like this, a small amount goes in and out comes a puff of steam. Another small squirt, another puff of steam. Now this is controllability. It's the addition of a precise amount of hydrogen peroxide, immediate response, giving off a small amount of steam and oxygen.
The Soviets fitted chemical motors similar to those pioneered on the rocket pad to their space station. These allowed the cosmonauts to give their ship a controlled burst of power to boost its speed and send it back into orbit. This way, the crew managed to circle the Earth for 23 days, a new world record.
I'm sorry, you go ahead, Dex, I'm out of the way.
It's day 3 of the shuttle's mission to deliver a new module to the International Space Station.
Okay, good switch. Okay.
Even after it has docked, the shuttle may be required to perform another crucial task. The International Space Station does not use its own thrusters to boost it back up to orbital velocity. Instead, it uses thrusters on a docked craft, such as the shuttle. The space station also has to constantly correct its position to keep its solar panels facing the sun. The panels provide all its power. To make these fine adjustments, astronauts rely not on rocket power, but on this, a gyroscope. Space scientist Kevin Fong demonstrates how a spinning wheel can move a space station.
This is a gyroscope. It's a very crude example of the sort of thing they have on space station. Now, like all gyroscopes, once it's up and spinning, it wants to stay where it is. And if you imagine that this plate here is the frictionless, weightless environment of space, if you can, and we get on top of it, if I turn the wheel, it steers me. And if I turn it back the other way and don't fall off, it turns me back again. And that is a very crude demonstration of how control moment gyroscopes steer the space station.
Engineers fit the International Space Station with 4 gyroscopes. As engineers on the ground adjust the tilt of these spinning wheels, they exert a force on the space station, which makes it move. The gyroscopes make constant tiny adjustments to ensure the craft's solar panels always face the sun, giving the crew the power they need to carry out their experiments. Astronaut Mike Fink has been on board the space station for 100 days. It's his second home.
So again, excuse our mess. We're in the middle of building a lot of things. We have my work area. It's a little bit cluttered right now, but this is kind of my desk. It doesn't sit out horizontally, but it has everything I need on it. Here's my crewmate, Yuri Lonchikov, exercising on the treadmill. Oh my goodness, it's beautiful up there.
Back in 1971, thrusters kept Salyut in orbit for 23 days. The Americans aimed to beat that record with an enormous laboratory in space. But first, they had to devise a way for their lab to stay in touch with Earth. In the late 1960s, NASA scientists planned a series of unique experiments to be conducted in space. Their laboratory would be a 100-ton space station called Skylab. Three astronauts were to be their human guinea pigs. The scientists wanted to investigate the tremendous toll that living in zero gravity took on the human body. They planned to monitor their experiments from Earth via a communications link. Spending time in space can leave astronauts without the muscle power to stand up when they return to Earth.
Space is a uniquely hostile environment, but one of the things that makes it very challenging is the weightlessness. There's lots of systems in your body that are dependent upon gravity just for their normal upkeep. your muscles and bones, but also your heart, which is essentially a muscle pump.
Without the constant force of Earth's gravity to work against, muscles like the heart begin to waste away. And the longer the human body stays in space, the more muscle power it loses. Scientists must overcome this problem for humans to live on planets where the pull of gravity is less than on Earth. The success of the Skylab mission relied on scientists being able to monitor the astronauts' vital signs from Earth. But there was a problem. Houston planned to use radio waves to communicate with Skylab. But radio waves only travel in straight lines. It would take Skylab 90 minutes to orbit Earth. So this gave the scientists on the ground a narrow window of just 6 minutes to monitor the crew as they flew over Houston. Not long enough to collect the data they needed. NASA needed to make their radio receivers mobile. So they fitted them to aircraft. Michael Kiley was one of the pilots assigned to fly these special planes.
Because of the capabilities of the aircraft, we could position these anywhere in the world based on the orbit of the spacecraft and able to provide real-time, continuous, full-time communications with the astronauts.
A 2-meter radio receiver dish was housed in the nose of the aircraft. Electric motors enabled the dish to move around so it could aim at any point in the sky. As the space station passed overhead, an operator inside the aircraft adjusted the angle of the dish to pick up Skylab's radio signal. As Skylab passed out of range of one aircraft, another took over. It required a fleet of 8 aircraft flying around the globe to maintain unbroken contact with Skylab's crew. Flying these aircraft required great skill.
You had to be in actual position for the spacecraft coming over the horizon with the antenna and the airplane pointed towards where the spacecraft was coming up. Track the spacecraft for as long as you could to get the maximum amount of data relayed back to Houston.
Thanks to pilots like Michael Kiley, the Earthbound experts were able to keep a constant check on their subjects in space. The scientists tried to strengthen wasted muscles by getting the astronauts to exercise against the resistance of elastic ropes. They gave underused hearts a workout by cocooning crew members in a machine that simulated the gravity of Earth. After enduring such trials for 84 days, the Skylab crew proved that the human body had a fighting chance of surviving without gravity. Today on the International Space Station, scientists have worked out that astronauts need to exercise for precisely 2.5 hours each day to keep their muscles healthy. But in this orbiting laboratory, the astronauts themselves are no longer the prime focus of scientific experiments. The astronauts are also investigating how crops might be grown and how animals might be bred in a gravity-free environment. As with Skylab, specialists on the ground keep in constant touch with the astronauts. Today, they communicate via satellite rather than aircraft. Nine satellites circle the globe thousands of kilometers above the space station. They are locked in orbit at fixed points around the Earth's equator. Together, the satellites give mission control almost uninterrupted contact with the space station as it orbits below. When the space station transmits a signal, the nearest satellite picks it up and relays it to Earth, from where it is beamed to mission control in Houston.
And go ahead, Koichi.
Appreciate if you could perform step 1.
And Koichi, that's not a problem. Thanks for the heads up.
Back in 1973, a fleet of aircraft allowed Skylab to stay in touch with ground control. But to make a bigger space station, it would require the marriage of two sworn enemies and the union of two incompatible spacecraft. In 1975, the United States and the Soviet Union made an announcement that shook the world. They would pool their resources to create a single space station. This joint effort was a symbol of the thawing of the Cold War and would bring an end to the tensions of the space race. Here was the plan. The Soviet Union would launch a Soyuz spaceship from Baikonur Cosmodrome in Kazakhstan. Simultaneously, the USA would launch an Apollo spacecraft from Cape Canaveral. Both craft would dock in orbit 220 kilometers above the Earth. Here, the American astronauts would meet the Soviet cosmonauts, and together they would conduct the first ever international space mission. One of the American astronauts was Vance Brand.
I thought it was going to be a very interesting flight with obviously an international flavor, a lot of challenges, something that we had to do right. But the bigger challenge was getting together with our well, I guess you'd say back then, our enemies, and pulling off a successful space mission.
But a huge engineering challenge also emerged. The Russian and American spacecraft were a mechanical mismatch. Both were designed at the height of the Cold War, behind a veil of secrecy. And in one crucial aspect, they were incompatible with one another. The air pressure in the two ships was completely different. The air in the Russian Soyuz craft was maintained at the same pressure as air on Earth. But on the American Apollo craft, the astronauts breathed pure oxygen stored at a much lower pressure. If the Americans opened the hatch, the sudden change in air pressure could have had a devastating effect on their Russian counterparts. It would have caused the nitrogen normally dissolved in their blood to reform as bubbles of gas. And these bubbles could have killed the cosmonauts. This condition also afflicts deep-sea divers if they resurface too quickly. They can prevent it by sitting in a chamber where the air pressure is gradually decreased. Engineers borrowed this idea and fixed a decompression chamber to the front of the Apollo ship. Once the two craft docked, the American astronauts would leave Apollo and enter the chamber. They would wait there for 3 hours until the air pressure equalized to match the pressure inside Soyuz. Then the astronauts would be able to safely enter the Russian spacecraft for a momentous handshake. On the 15th of July, 1975, Vance Brand and the Apollo crew set off on their mission.
Please don't forget about the
Less than 5 meters distance. Contact.
When we connected, why, there was a slight lurch and latches made, and there we were. We were elated. It meant that we'd gotten there successfully. Nothing had gone wrong, and we'd accomplished step 1 of our mission.
Step 2. The Americans waited for their bodies to acclimatize. Tensions ran high on both sides of this Iron Curtain.
When the hatch into their spacecraft was open, why, there were sort of cheers and shaking hands and hugging and all that. It was really a base that was put in place to improve future international cooperation, especially between Eastern Bloc countries and the West.
Welcome aboard Soyuz. We see that too.
It may be almost forgotten now, but we made steps that improved world relations, and we developed a pretty neat new docking system too.
This extraordinary meeting set the tone for future worldwide cooperation on the International Space Station. "350 kilometers above Earth, Space Shuttle Atlantis approaches the International Space Station.
Set. All right, here we go. In the center position.
The shuttle, loaded with its precious cargo, prepares to dock.
Moving it to the right about maybe 15 minutes or so.
Net dash 535.
Flight controller standing by for contact and capture of the International Space Station.
The new module has arrived safe and sound. So too has the multinational crew.
Hey, man, great to be here. Hey, Dan. Pulling a China shop.
The station has maintained a permanent human presence in space for nearly a decade. That's largely thanks to the engineers who have found a way to recycle humankind's most precious resource: water. At Marshall Space Center in Alabama, scientists have built a mock-up of a space station module to perfect the latest water recycling techniques. And they move civilian volunteers into the sealed chamber to live just like astronauts.
We use this chamber to help us generate real-life wastewater as representative as possible of the wastewater that the astronauts generate while they're in the space station.
Extractor fans suck in warm air laden with perspiration. and collect the sweat evaporating from wet clothes. The scientists give this sweaty fluid a polite name: humidity condensate. They also managed to recover the water in urine.
Urine, not surprisingly, is more contaminated than the humidity condensate. So we put that through an initial distillation process. We can recover about 85% of the water that's inherently in urine.
The recycling system on the space station manages to recover an incredible 94% of the wastewater produced by the astronauts. And the crew not only drink this water, they breathe it too. Inside the space station's life support system, electricity is passed through tanks of recycled water. This charge of energy splits the water into its chemical components: hydrogen and oxygen. Pumps channel the oxygen through pipes that run throughout the craft to carry the life-giving gas to the crew. Fresh air from sweat and urine. Back in 1975, the meeting of American and Soviet minds produced a spacecraft that was a world beater. But to move up to the next level, the Soviets decided to go it alone. To build an even bigger space station, they had to master the art of the spacewalk. In February 1986, a Soviet rocket took off carrying the first section of an enormous spacecraft. The completed Mir space station would weigh around 130 tons, far too heavy to be carried into space on a single rocket. So it had to be sent up in 6 separate sections and assembled in orbit by a team of spacewalking cosmonauts. The first challenge was working outside in such a hostile environment. Up here, temperatures can range from over 275 degrees in the sun to minus 275 in the shade.
Pictures or the swatch?
NASA astronaut Randy Bresnik reveals how a spacesuit fed with cold liquid benefits the spacewalker.
The liquid cooling garment is the mesh-looking with all these tubes. You know, a few 100 yards of tubing that actually have the water cooling that cycles through the whole thing that you can adjust to control your body temperature. So when it's, you know, minus 275, you can turn up the temperature and stay warm, and then when it's plus 275 degrees, you can turn the cooling up and cool down. So we need the suit to basically make a little individual spacecraft when you're outside to be able to do the work.
In early spacesuits, the liquid that cooled the cosmonaut, along with the oxygen he breathed, and the electricity that kept his systems running, were fed from space station to spacesuit through a long umbilical cord. But this cord posed a problem for the cosmonauts building Mir. Not only did it limit their maneuverability around the station, but if it snagged and sprung a leak, it could have spelled disaster for the cosmonaut. To overcome this problem, Russian designers removed the umbilical cord and replaced it with a portable backpack. It contained tanks of oxygen, batteries, and cooling and heating fluids that fed straight into the spacesuit. The designers supplied 2 of each component in case one failed. The cosmonaut couldn't bend his head far enough to see the control panel on his chest. So the designers thoughtfully supplied him with a built-in mirror. This way, cosmonauts could assemble Mir unimpeded. Despite their increased agility, it took them 10 years to complete the space station. But the new spacesuits made it far easier to build a structure of almost any shape and size out in space. Today at the International Space Station, the time has come to bolt on the new module, a prefabricated science laboratory. Astronaut Rex Walheim checks his spacesuit before his 7-hour spacewalk to fix the module onto the station's hull.
We copy the expected messages, and we're still just waiting on telemetry for Rex's suit.
To prepare for this moment, Rex has undergone over 200 hours of intense training on Earth.
Okay, copy. We're standing by.
This water tank at the Johnson Space Center creates a near weightless environment for the astronauts to train in.
We call this facility the Neutral Buoyancy Laboratory because in the water we can wear the same suit basically that we wear in space during our spacewalks, and the divers that assist us can add weights or styrofoam to our suits and make us neutrally buoyant, which feels a little bit like being weightless.
In the bottom of this pool sits a replica of the space station. Underwater, astronauts get to grips with maneuvering themselves around its hull. They have limited mobility in their spacesuits.
Is it a compression issue with the gloves?
Yeah, because I got a little bit of swamp in the tip of my gloves.
The cumbersome spacesuit makes even the simplest task, such as turning a wrench, extremely challenging.
His helmet is touching the lights here.
You had Dave for that port clamp and cutting all cables.
Back at the real space station, Rex's first task is to unload the module from the shuttle's hold.
Okay, so let me hold steady here.
The 10-ton laboratory may be weightless in space, but to move this awkward shape, he needs a helping hand. Luckily for Rex, the Canadian Space Agency has developed a special arm made from 7 motorized limbs. The arm is firmly anchored into portholes on the station's hull. A detachable hand enables it to lift objects and assist in construction. The crew use the arm to lift the laboratory out of the cargo bay.
Good job. Good motion. Continue. Starboard edge a little down, Dan.
The arm bends to line the module up with its docking port.
1 meter to go. Copy.
Rex then bolts the laboratory in place by hand.
We just stuck a little bit.
Okay, looks good, thanks.
In In just a few days' time, the laboratory will be up and running.
Thanks, Rex. Great job, guys.
In 1986, Soviet engineers cracked the problem of building in space and assembled a space station of unprecedented scale. But a structure as big as the International Space Station presents a new challenge. Its size makes it an easy target for accidental collisions. Today, the crew of the International Space Station live with the constant threat of being hit by a flying object. Over 100,000 pieces of discarded rockets and satellites litter the space station's path. This is a real-time image of the deadly orbiting space junk. NASA used radar to track the largest pieces of wreckage and steer the station out of harm's way. But the greatest threat comes from debris that's too small to see. Something as minute as a grain of sand traveling at orbital speed would have enough momentum to rupture the station's hull, cause it to depressurize and kill those on board. At Johnson Space Center, scientists can replicate such a debris strike. They load a tiny fragment of aluminium into a special gun and fire it at 25,000 kilometers per hour. At a sample of the space station's hull.
This shows a full sample. This is the impacted side, and this is the bubble on the back side. The bubble has basically burst on the back, like a balloon. Little pieces come off at high speed, like a hand grenade. So if you have, this would be the inside of the vehicle. If you have equipment here or personnel, and these pieces come off, it can be very damaging or an injury to the crew.
Engineers have found that one thick sheet of aluminium offers less protection than two thin sheets separated by a gap.
And you can see the entry hole there. The particle would come in and it hits this, and because of the high velocity that the particle is moving, as it goes through this layer, it shocks the particle, basically fragments it. And as it exits on this side, it's moving a little bit slower, but it forms a debris cloud. It looks like a kind of a balloon of particulate material. And that spreads out, and you can see by the time it hits the wall that we're trying to protect, it's spread out quite a bit.
To enhance this protective paneling, engineers pad the gap with the same material used for bulletproof vests, Kevlar. Now if an object penetrates the outer layer, the Kevlar takes the sting out of the cloud of debris, leaving the inner layer unharmed. Engineers fit shielding around the most vulnerable areas of the space station. They even fit shutters to protect the windows when they're not in use. Secure behind his aluminium and Kevlar shield, Mike Fink and his team can now get to work inside their newly fitted Columbus laboratory.
Here we are in the Columbus module, the pride of the European Space Agency. This is exactly how we work and live in space. And I hope you enjoyed the tour. This is Mike Fink saying goodbye and thanks.
The International Space Station paves the way for human beings to inhabit other worlds. It really is the ultimate spacecraft, until someone builds an even bigger one.
Next tonight on Channel 5, the Pistorius trial, the key questions.